Hello, guys. I hope you had a very good weekend. It was a weekend, I presume. So this is where we left off in the last class. Recall that we started considering sample spaces having equally likely outcomes. Yes. And those are just a set of universes where each universe is just as likely to appear as any other universe. And when you are calculating probabilities, you are solving two combinatorial problems, one for the numerator and one for the denominator. And you can choose the appropriate Kafka protocol to calculate number of universes of the desired type, that's the numerator, divided by the number of total possible universes. And even more, you can, because it's a ratio, you are free sometimes to choose different sample spaces, different sets of universes, because the probabilities, the ratio of desired universes over total universes will be the same. Yes? So that means, for instance, in this last example that we have covered with the balls in the urn and one being the golden ball, and we have to pick exactly k of them, we solved it under several assumptions, if you remember, right? Here is the difficult assumptions where I actually took into consideration every possible selection of k balls, and among them the desired golden ball. And then in the very last way we solved it is where we realized we can simulate the situation as if it were a pest dispenser, and all I have to keep track of is the location of the special ball in the first k places. So I completely ignored the selection or not selection of other types. Yes, guys, and the result is the same. That's what I mean, right? So the actual universe that happens, I presume, is where you pick a bunch of k balls, and then you have ball 1, 2, 3, 4, and maybe ball number n is there, and maybe ball number n is not there. But I switched to universes in which all I know is the space occupied by the special ball, and I can do that only because I'm actually calculating ratio. It ends up being the same ratio. Yes, guys? Wonderful. So here is another question. This is poker hand. We have to select 5 cards. There are 52 cards in total. And we want to know what's the probability of being dealt a straight. And a straight apparently is, we have what we have. We have consecutive values for the cards. So the card types are 1 through 13. And we have consecutive values for them, 1, 2, 3, 4, all the way to 13. And what has to be the case is that they are all not of the same suit. So they have to be consecutive and not all of the same suit. What's the probability? I'll give you guys very little time, just maybe 1 minute, 2 minutes. Try to calculate it, and then we'll do it together, yes? And turn on your screens, guys. And more and more of you think that it's not necessary, but yes, I would like to see you. Gustavo, make sure that you don't confuse what ratio, which order of ratios we have, right? We place number of desired universes divided by number of all available universes. Again, guys, we have 52 cards and we pick only 5. Make sure that we pick only 5, and the cards that we pick, I could rearrange them so they would be consecutive. I didn't say they are picked one after the other in order. I said that the cards that you have in your hand, you're having 5 cards, you can arrange them from smallest to largest in consecutive order. Clear? And they cannot have the same suit. In other words, if you look at the back, they are not all hearts or all spades. Very good. All right, let's do it together, guys. So the first question you have to ask yourself is, what is a card for a bureaucrat? Right? I have to visualize a card. How do I record information about a card? No, a card has 2 sides. Do you agree? So I can imagine numbering hearts, spades, diamonds, whatever else you have there, 1 through 4. So on one side, I imagine the number 1 through 4. And on the front side, the number is 1 through 13. You understand? So I personally don't play cards, but because it's against my nature, if I play it, it will be like in Dostoevsky's Gambler. You should read that book. So the front number is 1, 2, 3, all the way to 13. The back number is 1 through 4. Those are the codes, back and forth. So a card is a pair of numbers. Do you agree? And so when I record them in my protocol, in my document, I have to record the pair of numbers. So what has happened? So let's look at the, let's look at the sample space, right? So for the sample space, I can describe the cards simply by their population code. The population code of the cards is just 1 through 52. Do you agree? I mean, I can just imagine that the cards have 2 ID numbers. You know, ID numbers become very popular these days. So the cards have the population ID number 1 through 52, and they also have the pairing. We can identify them by front number and back number. Now, it's convenient to just say the possibilities are 52, choose 5. Do you agree? In other words, all universes I can record for the sample space based on their population ID, and I will just generate 5 numbers, 5 distinct numbers, and I will place them in increasing order. Right, so you agree when you choose a bunch of people and each person is labeled 1 through 2, 3, 5, 6 all the way to 52. I can record those people based on the smallest number that was selected, next smallest, and so on. Agreed? So this code is easy to write. Notice I have those incomplete lines here to indicate that I place it in order, and that's 52 choose 5. Everybody understands this part, yes? Denominator is easy. Now, how do I describe the situation where I select successes, right? Successful universes, I selected cards that display frontal consecutive sequence, right? So frontal consecutive sequence can be described by first smallest number, right? By the smallest number. Was the smallest number 1? Then the largest number was 5, right? 1, 2, 3, 4, 5. Well, the smallest number was 2, the next would be 3, 4, 5, 6, right? And onwards, right? So, so how many possibilities are there? So this is my document for success. E is the successful universes where I drew a straight. So what's the situation? The situation is that I'm allowed to place here any first number, and there are 13 numbers in total. So the first number is 1 or 2 or 3, and the total numbers I can place is 13 minus 5 plus 1, or 9 numbers, if I understand it correctly. Yes? You understand why I do this, guys? Because if I picked 5 consecutive cards, the smallest cannot be number 13. Do you agree? Because after 13, I don't have cards to pick, or cannot be number 12, or number 10 cannot be that, right? The smallest, the largest, smallest number we can have is the number 9. So that's 13 minus 5 plus 1. You understand why I subtract 5? 13 minus 5, it means that from the largest number, I go 5 down, and I add 1 to include the smallest number that I pick. So it's 13 minus 5 plus 1. Agreed? So, yeah, so once I have, I record this number here, I can imagine the cards are arranged in order, and I can say, what is the suit for card number 1, suit for card number 2, 3, 4, 5, right? What are their suits? So the suits, they're distinct cards. You agree? So this is 4 possibilities, 4 possibilities, 4 possibilities. It's 4 to the power of 5 ways of placing a number here. Now, what happens to be the case, they cannot be of the same suit. Do you agree? So I cannot place all 1s, or all 2s, or all 3s, or all 4s. And that's why I subtract 4 possibilities, right? The minus 4, that corresponds to the codes 1, 1, 1, 1, 1, or 2, 2, 2, 2, 2, and onwards, right? So I remove them. So it's 4 to the power of 5 minus 4. Everybody agrees? And so what do I get? I get, so very easy. Do you agree, guys? If you understood, if you follow, that's why I want you to do all the Kafka protocol, is that you think deeply what something means. How do you record that information? So you should see a form, and that form tells you, if I see a code there, can I figure out what was the outcome? If the situation is so, and every outcome can be recorded as a code, you just count by basic principle of counting. You can just use those properties. And this form tells you precisely how to do this counting. That's why I am able to do it. So the answer is 9 multiplied by 4 to the power 5 minus 4 divided by 52 choose 5. So the probability appears to be roughly, well, I mean, to exaggerate it, 4 out of 1,000. By the way, guys, how is my internet going? Is it good? Yes. I think I'm connected to the cord, so hopefully that's right here. Let me just check again. So somebody asked to repeat it. So do you all see the success form that I created? Not getting the front and back. Okay, Sydney, thank you for letting me know. Front and back, guys, right? I assign codes. That's what I do, right? I assign numbers to any situation, right? Codes. So what is a card, right? So for instance, what is an ace of spades? Ace looks like 1. Maybe ace is 1, right? So front number is ace, it's 1. Spades, let's say maybe it's the number 3. Maybe I have hearts, diamonds, spades. So spades is 3. So then this front is the number 1, back is the number 3. If I assign codes like this, then when I say 1,3, I am talking about ace of spades. That's what I mean by front number and back number. So I number the suits. I imagine having numbered the suits. Does it make sense, guys? So to me, mathematically, a card is a pair of numbers, front number and back number. And when I describe which cards were selected, I need to say front number and back number. That describes the card. Good? Everyone is clear? So that is my success form. So this describes the first frontal number, and this describes in order, the back numbers of the cards that I selected. So this is a success form. In other words, if it was a success, it doesn't work for non-successes, right? If I had 5 consecutive cards, what must be the case? It must be the case that I selected consecutive frontal numbers, let's say 1 through 5, or 2 to 6, or 3 to 7, right? So the biggest first number I could have selected was 9. That's why the possibilities for this smallest number is 13 minus 5 plus 1. Good. And then if I place them in that correct order, first order, smallest card, that's the smallest frontal number, second smallest frontal number. What's the suit? 4 possibilities for the suit, 4 for this, 4 for this, 4 for this, and 4 for this, 4 to the power 5. But there was an extra requirement telling me that I cannot have all suits the same. So I cannot have 1, 1, 1, 1, I cannot have 2, 2, 2, 2, and onwards. So that's why I subtracted 4 possibilities. That's to remove codes that are a string of 5 digits 1, a string of 5 digits 2, 5 digits 3, 5 digits 4. Do you understand, guys? Everyone's clear, right? So the answer that I obtain is approximately 35 over 10,000, or roughly 4 over 1,000. So it's not very likely, right? 4 over 1,000, it's not a likely number. Yes. So here is your next example, guys, and let's see if you can help me. So again, we play with cards, very good tool to train yourself on. And here I want you to tell me what's the probability if you're given 5 random cards, what's the probability that you will see 2 cards of the same number, frontal number, and all the other cards are distinct. So solve A. Understood? Very careful. Make a Kafka protocol. Gustavo, you're absolutely right, but not specific. You're like Nostradamus. Ryder, keep your comment. In a moment, I'll address it. Hopefully, I'll address it. So I won't forget it. Okay, you'll ask me once I'm done with this problem if it relates to it or the one before. ABC are numbers. I mean, strictly speaking, they are letters, Nicholas, right? I think it goes to elementary school. A, B, C, D, E, F, G. All right, guys. I guess let's do it together. And guys, definitely stay after class. You know, I'm hopeful that you will learn probability, right? I mean, not just survive this class, which is way too easy, because I'm just going to close my eyes and pretend that that I don't see that you're cheating, maybe, right? Which I do. It gets very hard to not notice it. You know, I really feel it, and I cannot sleep at night. So let's understand it, right? It will be much more pleasant. So this is the situation, guys. So first of all, there is no problem about the denominator, correct? Denominator is 52, choose 5, agreed? Now let's make ourselves a Kafka protocol for the numerator. What happens here, guys? We select we select one pair, sorry, right? One pair means that we have the front number of the card repeats twice. And all the other cards do not have a repeating frontal number. Good. The lowest number would be 11. Let's just before we go there. So here is A. Here is my document. Agreed? This is my document. So there is this number and the suit. So what goes in here is the number on the pair. If I select, if I'm successful and I selected one pair, what is the front number on the pair? Do you agree? Is it number 1, 2, 3? There are 13 possibilities. 13 choose one possibilities, and because it's a pair, there would be two different back numbers, right? So that would be 4 possibilities and 3 possibilities. And notice that I will arrange, once I have two pairs, I will arrange them in such a way that the back numbers, if the front number is the same, the back numbers will be arranged from smallest to largest. You with me? You see how I'm thinking, guys? Are you thinking the same? Are you able to see what I'm doing, right? That's the only reason I'm able to do it fairly quickly, is that I'm able to think this way. Very concretely. Yes? You see those three boxes. Those 3 boxes tell me everything about the pair selected, nothing else about other cards. Do you agree? Because if I selected one pair, what does it mean? I have two cards, and on the front I see the same number. But if I turn on the back, then that's not the same number. You agree? One is spades, the other is hearts, for instance. You agree? So a pair means the same front numbers. So what is that front number? 13 choose 1, 13 possibilities. Is it card 1? Is it card 2? You know, front number 1, front number 2. And then what is the possibility here? 4 choose 2. You agree? Because basically what I can imagine is, if I have 2 cards, and imagine that this is 1 and 1 on the front, and on the back it's 2 and 4. So I will place the card with the 2 on the back. I will place it here, and the one on the with the 4 on the back, I'll place it later. I place it in order. Do you understand? I place my cards in order. So if it's the same front number, I use the back numbers to place them in order. Is that clear? It has to be very clear. So then this thing is 4 choose 2. Now, how many remaining front numbers can I have here? There are 12 remaining front numbers available, because I cannot use that number from the pair. I have to use other numbers. There are 12 available, and I must choose 3. Do you agree? Because Other front numbers are not the same. So I choose 3. So I have 12, choose 3. Yes. And then for this card that I choose, what is the suit? 4 possibilities. The second has 4 possibilities and the last has 4 possibilities for suit. You understand? Because I only specified which front cards I picked. I placed based on the front. I place in order, and then first single card, what's the back number? Second single front card, what's the back number? So what I have is 13 choose 1, 4 choose 2, 12 choose 3, 4 cubed. Are you with me? Yes, right. Why or if you're confused, guys, I'm happy to re-explain. Yes.
So I think I get what 13 choose 1 is. There are
Yes,
13 possible. There are 13 possible numbers, so you have to choose one of those.
Mhm.
And there are 4 of each number, and you have to choose 2 of those.
Mhm.
And then I don't know where you're getting the 12 choose 3 from.
Okay, good. Thank you.
Yeah, no, almost there. And then
It's because I want to specify all the cards that I chose, right? So what happened? Success means I chose one pair. What was the number on the pair, and what were the suits? You see, so those boxes tell me the number on the pair and the suits. Now I had to choose the other 3 cards, right? The other 3 cards here. Here they are. They have different front numbers. Do you agree? They have different denominations. What do we call it? So I cannot use the pair denomination. I have to use a different denomination. Yes. So I will take 13 was used. I used 1 card. So I now have 12 available denominations left. Out of those denominations, I have to choose 3 because they will be distinct. Yes. And once I choose those 3 denominations, I list them in order from smallest to largest. Yes. Can you see it?
And is that what the 4 to the 3rd power is?
That's for their back. So first I list their front values. The front values on the cards, I list them in order. Yes, I list them in order, and then for the suits, I ask myself then what's the suit value or what's the suit number for the first card? What's the suit number for the second and the suit number for the third based on denomination? I arrange them by denomination, frontal number, smallest to largest, and then I describe the suit. So that's the 4 cube, because this card could be any one of 4 possibilities. The second card could be any one of 4, and the third could be any one of four of its kind. For each front number, there are 4 of the kind, right? There is ace of spades, there is ace of hearts, there is ace of diamonds, right?
Okay,
so
I got it. It suddenly clicked. I get it.
I hope so.
Thank you.
Right, and if not, guys, you stay after class. I will explain it much slower. I'm only rushing because in previous semesters when I do it online, I end up really not having enough time to cover the material. The class is too short. It should be like 4 hours a day, I think. And then we can stop and spend like 15 minutes for you to think about it. But unfortunately, I can't do it during class. Good. So I'm sorry about it. And if you have questions, trust me, I will answer them if you stay after class. Good. So then the second part, guys, can you try to solve B?
Okay, let's see what's down. This thing. So it's
Very good, Gustavo. I'm very happy. So train first to make Kafka protocol. Eventually you can do it in your head, but first actually write it out so that you see that what you're doing is necessarily right. Steven, maybe is it 48 or less? Let's say you need to remove, because you need to remove all those cards of the same category, not just 4 cards. You need to remove 8 cards. 44, I think. Right? Mm-hmm. Very good, Camille, wonderful. Very happy. All right, guys, let's do it together now, I guess, right? So again, what is my success protocol? So success protocol has values on pairs. Look at it, you see, this is the way I decided to make it. First pair, smallest pair, and larger pair, and then the suits for the small pair and the suits for the large pair. So those 2 boxes here, they refer to suits for the value on the first pair, and those 2 refer on the value on the second pair, and this talks about the remaining card. I decided to make it the remaining card. Yes, I could have done it also just as there, just the remaining values available and the suit. So both work. Yes, Chiari, let's see, very good. I think, right?
Why is it 52 minus 8? Choose 1.
I think 11 choose 1, right? Not 10, but 11 choose 1. Aside from that, I think, and then on the denominator choose 5, right, Chiari? But aside from that, all good. So this is the situation, guys. You see, 13 choose 2. The 13 choose 2 refers to pairs. So whatever number when I choose 2 front numbers, I know that this front number corresponds to 2 different suits, and the second bigger front number will correspond to 2 suits. So that's where I have 4 choose 2, and this is why I have 4 choose 2. And then in my form, I have I cannot use any of those 8 cards. Basically, any numbers here I cannot use. So I cannot use the 2 numbers that were selected, and that means I cannot use 4 cards. And I cannot use the numbers that were selected here, and another 4 cards I cannot use. So it's 44 here. Or you can instead just have a box. It's 11. So we have 13 choose 2, 11 denominations left. So 11 choose 1 and choose a suit for that one. So it's 11 times 4, right? Also 44. Same thing. Do you understand me, guys, or do I need to write another Kafka protocol? You understood what I did, right? Here I mixed it up. I decided to refer to the last card by its population number rather than by front and back number. That's okay too, if it's precise. But I could have done it as front number any one of 11, back number any one of 4, and I will get the same result.
Right, because the last card can still be a match for the other ones. It just won't be one of the pairs. You'll still have 2 pairs. Although you also have 3 of a kind.
Yes, I mean, 3 is not going to be considered a pair. So you think this example is
specified
simpler
that.
than this one, and the
But
previous
you
one?
did say that the last number can't match the other 2.
Right, the numbers cannot match. We have to have 3 different numbers. 2 of them
Okay.
assigned to pairs and 1 assigned to a triple. Good. So this is what we have here. I'm hoping you're getting it, guys. Yes. So I tell you that I would make tons of mistakes unless I kind of thought of it this way, very organized in a form and counted what's in the form, because then I know that I didn't miss anything and I'm multiplying the right numbers. So here is another example. Poker dice is played by simultaneously rolling 5 dice. What's the probability of 2 pairs? So it's like the previous question, but now it's based on dice. What do you think? Probability of 2 pairs. So here you can see how a solution could have come about. Careful, Gustavo. Why 6 choose 5? They're not cards, that's right. Try to write yourself a protocol, and the protocol has to tell you what are the general possibilities first for the die, and then what are the possibilities for success. On the denominator, yes. This, you can make it so. So, Stephen, your numerator is good. Let's see, am I right? No, numerator, there's something wrong with numerator. No, not good. And denominator, why is it 13 choose 5? 30 choose 5. Okay, give me a second to. Okay, Gustavo, 6 choose 2, then why 5 choose 2? All right, let's do it together, guys, and see at least how I think of it, and if hopefully. So first of all, let's look at the denominator. Okay, guys, it's important to do the experiment in the same way you do the denominator. So I assume I can see the dice. Let's say maybe they're different colors, or I know which is die 1, die 2, die 3, die 4, die 5. They're unique, right? For the calculation of probability, they are objects in the same, not in the same space at the same time, so they're different objects. So I can imagine there is something distinct about them. So this is These are my dice. And so the unconditioned outcome on them is 6 possibilities on die 1, 6 for die 2, and onwards. So it's 6 to the power 5. Do you agree? That's for the sample space. If I do it this way, I know that I have 6 to the power of 5 possibilities. Right, where the number displayed in box 1 is the outcome for die 1, the outcome for die 2 is here, and onwards. Good. Now, what is my protocol for success? So this is how I decided to make my protocol for success. So then I want to know, first of all, which pairs did I get, right? What are the numbers on the pair? So 2 dice are displaying the number 2, and 2 dice are displaying the number 4. Here is basically the situation, guys. You see, imagine this happened, okay? Do you agree that it's 2 pairs? You can see here is 1 pair, and here is another pair. Agreed? Now, how do I record that situation? So I need to know in the situation which pairs and which singleton were selected, what numbers were selected, and which die displays those numbers. Are you agreeing with me? Which dice are actually showing the numbers. So let's see if this code works. You agree that? Look at it. So how do I write this information into my boxes? So the pair values, smallest pair value is 2, larger pair value is 4. Agreed? This information is not enough to know everything, right? And then of course I need to know that 1 die is displaying 3. So those are the numbers, 2, 4, and 3. Now, that only tells me which values are displayed and how many times each value is displayed. I know 2 dice are displaying the number 2, and I know 2 display the number 4. And I know 1 die displays the number 3, but I don't know which ones yet, yes? So then in the next box, I tell you which one displays which category. So you see I have this dotted line here. Dotted line tells me everything below the first dotted line tells me which dice display the smallest pair. Between the 2 dotted lines, which 2 dice display the larger pair. And the last number tells me which die displays the number 3, displays the singleton value. You agree? Now, if you read this code and you understood how this information was placed together, you could have reconstructed that this was the outcome. Do you agree? Do you agree, guys? Yes, you see what I do. So for instance, 1 and 3. 1 and 3 display the number 2. 1 and 3 display the number 2. You see that, how I read it? 4 and 5 display the number 4. So 4 and 5 display the number 4. Die number 2 display the number 3. Die number 2 display the number 3. So my code works. You could come up with different codes, but the point is my code works. So then I have a protocol for counting all of them. You agree that this form will allow me to deconstruct or reconstruct, sorry, the actual outcome. And if I have an actual outcome, I can place it in the success code. Agreed? So then how many ways to create this code? Well, how many ways to fill in the 4 pairs? There are 6 values and I need to pick 2 of them. I will explain, Gustavo, I will get there. That's to count this thing, right? But first, do you agree that there is 6 choose 2? 6 choose 2. Yes. And then for the singleton, I cannot use the pair values. I need to. I lost 2 values from selection, so I have 4 available, and I have to take 4 choose 1. I selected 2 values, so they're no longer accessible. I have now 4 choose 1, 4 possibilities for the singleton. Yes, so that only is the information that tells me which values are displayed, but not which die display them. So it's not complete. Yes. So then how many ways to display those values? Well, the 5 here refers to the die. They have die number 1, 2, 3, 4. So the dice are now assigned destinies. So what it means now is that 5 dice, 2 of them are assigned to carry the smallest pair. 2 are assigned to carry the larger pair, and 1 is assigned to carry the singleton. You agree? So the values on the die are my dragons, and the knights are the dice here. So you understand? So that's where the Gustavo, that's where 5 choose 2 to 1 comes from. You see, why? Because I'm assigning the dice, I'm assigning their destiny. So there is a destiny of 2 of the dice to display the number 2. 2 of the die will display the number 4 in this example, and 1 will display the number 3. So in general, and this is what happens, right? So for whichever values you have here, you have this distribution, this assignment of destinies. You can figure out other ways of doing it, but that's a convenient one. So what is that value? That's the same as 5 factorial over 2 factorial, 2 factorial, 1 factorial. And this you know how to calculate. And the probability is not too low, guys. It's 23% more or less. So it's 3%, 23% likely that that 2 pairs will be displayed. Are you with me? And let's do one more example of the same sort. Ready? So now we have 9 dice are simultaneously rolled. Yes, Grant, you understand? It's just a matter of thinking very clearly what information are you seeing and recording it. So it actually makes you think very clearly. That's very, very good. Clear thinking is very, very pleasant when you get there. So 9 dice are simultaneously rolled. What's the probability of getting 3 pairs and a triple? So I drew it over here. You see, this is the situation. Not necessarily in this order, naturally. Hey, Gustavo, yes, so interesting. Correct. There is also this, Gustavo. You say 6 choose 2, and then 5 choose 2. Why 5? And you have to be very, very careful with those things. Make a protocol, guys. You see, so that the protocol will tell you if what you're counting even makes sense. Because if not, you might be confused about a lot of things. Okay, Nicholas. I don't see the pair choices. I mean, maybe no, maybe you're right. Let's see. So it's 3, and then the remaining one. 6 choose 3 should be the pairs. Okay. Okay. I see. Yes. Good. All right, guys. Let's do this together. So again, denominator is clear, right? I imagine I see 9 distinct dice, And the possibilities are then 6 to the power of, sorry, 9, no, sorry, 6 to the power of 9. Do you agree? Because 6, then 6, then 6, 6 to the power of 9 is the denominator. So 6 to the power of 9. Now, yes, Nicholas, as you can see, you are right. Now, what are the possibilities for the pairs? We have, we need to select 3 pairs. Do you agree? Very good, Barry. 3 pairs. So 6 choose 3 are the values for each pair, and I will place them in order: smallest pair, middle pair, largest pair. And then 3 choose 1 for the triple. Do you agree? So altogether, that the first boxes tell me only the numbers displayed, nothing more. So that's 6 choose 3, 3 choose 1, and then I need to decide which die display them. So 2 of the die will carry the smallest pair. The next 2 will carry the middle pair. The next 2 will carry the largest pair, and the last 3 carry the triple. Yes. So then the formula becomes 9 choose 2, 2, 2, and 3. You see that smallest pair, middle pair, large pair, triple. Good. And this is the number that I get. Agreed? Now, you can do it differently. You can, for instance, here let me ask you this question, guys. And you tell me if it's correct or not correct to do it this way, right? So how about this? We select the first pair, right? First pair, we have 6 choose 2. You agree? 6 choose 2 for first pair. Then 4 choose 2 for the, or should I say that? No, sorry, not like this. I meant 6 values for the first pair, then 5 values for the next pair. Yes, and then 4 values for the last pair. Yeah, and then we have this this 9, and then we have the remaining values for the triple. The remaining values for the triple, so times 3, and then we have 9, 2, 2, 2, 3, or 6 to the power of 9. Is this a correct solution? Looking at what I did here, so I said 6 possibilities for the first pair, 5 possibilities for the next pair, 4 for the next, and then 3 remaining 3 values available to be represented for on the triple. Yes, is this correct, or is something wrong here? The pairs. Yes. So notice, guys, what can go wrong here. What can go wrong here is it's in here. That's what can go here, right? So so because what this indicates about the protocol is, for instance, suppose that I can this will count the situation. Suppose that I select number 1 for the first pair, whichever first pair means, and then number 3 for the next pair, and then number 5 for the last pair. Right, so that is a separate event from selecting 3, 1, and 5, for instance. It's a separate event. You understand? In addition, it is also, what do you mean by first pair? You have to be clear. When I say first pair, what do you mean by that? Is it how do you identify when you read the code? How do you identify what first means? You see, so there is an ambiguity here, and whenever there is ambiguity, you should be very wary. That might mean that you are miscalculating something, because you haven't described how the code is produced to begin with. And incorrect, this code is you can see that whatever it is, I could have, if I write boxes, I could have written the numbers in different orders. So it's not organized, and of course can create mistakes. But isn't 6 choose 3 Well, 6 choose 3 is this. It's 6 times 5 times 4 divided by 3 factorial, Stephen, right? So if you divide by 3 factorial, then that makes it correct, because then you eliminate reorderings there. But even when you say it makes that correct, there is a problem in thinking there. It's hazy, guys, right? If you say 6, 5, 4, what do you mean? What's the 6 referring to? What is the 6? 6 possibilities for the first pair is vague. You agree? What you should always imagine is a situation where you look at what happened and you're able to record it. And that means that your recording of it is unambiguous, that people understand how to read it. You're counting codes. Is that clear? So you can make many, many mistakes if you are not clear on what is it that you're counting. All right. Let's move on. Now we talk about the game of bridge. So in a game of bridge, 52 cards are dealt equally to 4 players. What's the probability that one player receives 13 spades? What do you think? You see, guys, so you take 52 cards and each player gets 13 cards. Now, one player is supposed to get all spades, all 13 spades. What's the probability of that happening? Calculate. All right, guys, make sure that you account. That's the very important. Make sure that you're accounting what goes on. We can solve it several ways, right? You can ask yourself, do I need to consider other players or not? Yes. So maybe we'll solve it in 2 ways. I see some suggestions here. You just need to solve probability, right? So you might need to account for it or you might not need to account for it. Good, Gustavo. Okay, see if you can correct it. No, maybe you don't have to, Gustavo. But try to figure a way just in case. Well, let's see. Stephen, something about your denominator is too small. All right, let's do it together. Let's draw a Kafka protocol. All right, guys, so what actually happens here, right? So you have player 1, player 2, player 3, player 4, you agree? And they can, in general, get any 13 cards. You agree? So I'm gonna do it in two ways. So method 1, I account for everything. Account for everything. Well, so let's see, Grant, 1 second. So accounting for everything means, first of all, sample space. How do I code for sample space? So for sample space, we have a box containing 30. That's for player 1. We have another box, player 2, and onwards, right? Can you see it, guys? So what happens is that you give the 13 cards to player 1, player 2, player 3, player 4, and they will arrange those cards in order. We're using population numbers. So I'm not considering front and back number. I'm just considering the cards as labeled 1 through 52. Do you agree? And then in the denominator, they will be instructed to record the cards in order, right? So how many possibilities are there? That's the knights, and that's 52 cards. 13 of the cards go to player 1, 13 go to player 2, 13 to player 3, 13 to player 4, and the answer is then 52 factorial divided by 13 factorial to the power of 4. You understand how that works? So make sure you understand multinomial coefficients. Yes, guys, you understand the idea. So the cards 1 through 52 have destinies. They either go to player 1, player 2, or player 3, or player 4, and exactly 13 of them will go to each. Yeah, so you should understand why this formula is made. Yes, if that's the sample space I use, I'm stuck. Notice here I decided to account for every single player. If I decided to do that for the denominator, I must do the same for the numerator. Yes. So what's the success form? The success form would be, okay, given that one player received all the spades. Spades are labeled as 1, right? Spades are 1, and others are labeled 2, 3, 4. Yes. So which player received all spades? So first box, the player of spades. Let's say maybe player 2 received them, right? Player for spades, there in general here 4 possibilities. Do you agree? Either player 1 or player 2 or player 3 or player 4. Yes? So I know which player received the spades. Now, how many cards do I have left? I have 52 minus 13. So I have 39 cards, correct? 39 cards are remaining, and they must be distributed among people, among the remaining players. So then I have here a box for player, whatever, the remaining player. And another box for player. Though those are the remaining players that do not include the spade player, right? So that makes it, what? That makes it the situation 39, 13, 13, 13, which is 39 factorial divided by 13 factorial to the power of 4 times 4, right? Times 4. So that makes my number. I hope so, Grant. So what's the answer? The answer is 39 factorial divided by 13 factorial cubed divided by 52 factorial over, well, I should mention there is a 4 here, divided by 13 factorial to the power of 4, which simplifies to 4 times 39 factorial divided by, well, that, and then times 13 factorial, right? Divided by 52 factorial. Good. That's a small number. Now, let's think about the situation, guys. Do we really need for problem A to consider the other players? Right? We don't have to do that. You agree that what happens here is that one player receives all spades, right? Now, what's the probability that a particular player, player number 1, receives all spades? So we can do it also this way. I just have to be careful. So possibility 2, I'm only interested in one player receiving 13 spades, but the player can receive any 13 cards. You agree? So let's say probability player 1 receives it. So just for player 1, what's the probability player 1 will receive the spades? That would be, for sample space, then 52 choose 13. You agree? Because he can receive, just by symmetry, there is no preference to the cards that he will receive. He can receive any 13 cards, right? What's the likelihood he will receive all spades? There is only one choice of 13 cards that works, right? So it's one choice. Agree? One of those 13 choices captures the 13 spades. So the answer is simply, for E, there is only one possibility. So for player 1, the probability that he will receive all spades will be 1 over 52 choose 13. Yes? And of course, we want to add to it the probability that player 2 receives it, right? And player 3 receives it. Those are separate events. So we can have a pile of documents representing the situations, universes in which player 1 received all the spades. And then we have the same pile, same size pile for player 2 and for player 3 and player 4. They are disjoint events, you agree? So altogether, the answer is 4 divided by 52 choose 13, which is what? Which is 4 divided by 52 factorial over 39 factorial and 13 factorial. Yes, which results in 4 times 39 factorial times 13 factorial over 52 factorial. And the answer is just the same as we obtained before. You agree? So you understood what we did here, guys. We narrowed down the possible universes. Here we only considered one player instead of everyone. How about one last question before we go? Now, can you answer question number B, guys? So each player receives one ace. What's now? Ready? Okay, Nicholas. Interesting, right? So the probability, but you have to be very careful. I think you ignore several possibilities. Nicholas, I like your guess. It's very nice, but the problem is, the problem is that they don't have to receive aces this way, right? So here is how you can solve this question. So which aces do each of them receive? So player 1 receives 1 ace, player 2 receives 1 ace. There are 4 factorial ways of arranging the aces. You agree? I didn't draw the Kafka protocol, but I hope you imagine what I see is player 1, player 2, player 3, and the ace they receive separately, because that's the success protocol. So there are 4 factorial ways to assign aces to them. And then they will get 12 cards each. So 48, choose 12, 12, 12. And the denominator is as before for the population. Now there is a Nicholas, I would not agree with your calculation. What you wrote over there is that they don't the aces cannot, they don't have to be distributed just they could be all going to one player, or some of them distributed among 2 players. You understand, it's a bit complicated. So maybe there is a way to eliminate something more, but it's not immediate. So only do something when it's absolutely clear what happens. You understand what happens in this situation. Good. All right, guys. I wish you good night. Of course, if you want to stay after class and talk about something, I'm still here. If you have questions. I'm going to stop recording.